Right, welcome back. We're gonna go over problem 2. Not so actually be this one is problem 2. Other than pretty much homework, but it is homework 9. Okay, so this is telling us to do is say we have that second order low pass filter right here, and they're telling us to find a transfer function of this filter. What we usually do in finding these is we change it into impedances and we go from there. So let's actually do that. We have the Vn. We're gonna do the impedances of each one of these. Yeah, C becomes 1 over j omega c. L becomes j omega l, and that would be a value of r. So I'm just going to write r right here, since these two are in parallel. What do we get from doing this? Let's see, the best way to showcase this one will be, yeah, let's calculate this parallel thing, because we know it's going to be, the out is going to be between these two terminals, and these two are shared. So say A and B, this is A, and this is B still. Let's find impedance between A and B. R multiplied by 1 over j omega c divided by r plus 1 over j omega c. This becomes r over j omega c. This denominator becomes multiplying by this becomes j omega r c plus 1 over j omega c. We can cancel out, since both of them have j omega c in the denominator, cancel out that term, and the c equivalent, let's say, load becomes what? R divided by 1 plus j omega RC. Now we can simplify this to j omega L. What we have right here is the equivalent load. And now we can just use the voltage divider, which is the out is right here, A and B. So it becomes the out j omega divided by the n of j omega, which could be referred to as h of j omega usually, is equal to the equivalent divided by j omega l plus the equivalent. Yeah, I know this is really nasty. Let's see what we could do. Okay, so let's just write it down and see what it comes to. Plugging in or the equivalent of load r over 1 plus j omega RC divided by j omega L plus r divided by 1 plus j omega RC. This actually leads us to dividing the multiplying both denominator and numerator with 1 over j omega RC. You know that this one will cancel out, this one will cancel out, and what I'm going to have is r divided by So when I get a j omega L plus j omega RC times j omega L. So I know that it just becomes j omega squared times L times R times C, and I have to add a R to it. So yeah, we can leave it at that expression, or we could simplify a little bit further to make it easier. Let's say this is the answer. Change it to red. Oops, didn't change. Or I could divide the numerator and denominator by r, and that way I'm going to get something like this. 1 divided by j omega L over R plus j omega squared. We could write down instead of j omega squared minus omega squared, because j squared is minus 1 and omega squared is omega squared. And the r cancel out right here, so it becomes LC and a 1 right here because r divided by r is 1. Now, let's move on and see what else we have. Part B is asking us to calculate the damping factor and everything else. Let's paste this, make it bigger, bring it up here, and we asked to find a expression for Q factor and the damping factor. Usually how they do it is we know that we can write the above expression like this. So we know that j omega L over R is just going to give us a 2 times this psi times 1 over omega naught plus j omega squared divided by omega naught plus 1. Now, how do we figure out what C is, and so on. So if you come back right here, you know usually how to define the frequency where omega naught is 1 over square root of LC is equal to omega naught, the resonant frequency, is what they call that, undamped natural frequency. And the damping factor, or E epsilon, that we found right here, writing this down, C or psi, whatever you call it, is just going to be a 1/2 multiplied by L over C divided by R. So if you want to go back to this expression right here to getting back L over R, you just plug in these values back and just gonna do a quick check for you. 1 over 2, 2 times value of C, so it becomes square root of L divided by square root of C times R times 1 over omega naught. Remember, omega naught is this, so it just becomes square root of L times square root of C. And now you can cancel out the C's. q's, and then L times L, square root of L times L becomes L divided by R, and we got the exact expression we had above there. So, just to do a quick check for everybody. And now I'm going to remove that. And now let's find the Q factor. Q factor is going to be 1 over 2 psi. And let me just go writing it like that. I'm having a hard time coming with this symbol sign they have right there. So 1 over psi. So now you do know that the q's will cancel out. 2 times 1/2 is cancels out, and then what I'm going to have is r divided by square root of L over C. We could write it down as R times square root of C over L. And if you're wondering if you wanted to write Q in terms of omega naught and so on, and have the value of R in there, what you could do is you could, let's see, how to go about this. Something that I remember. All right. So let's see. Omega naught is square root of LC. So L is in the denominator already. So let's see. Let's rewrite this. R times square root of C divided by square root of L. So if I do multiply and divide by C, so I could write square root of C times square root of C. This is basically a value of 1, right? C over C. Then I can cancel this with this. I'm going to be left out with R times C times 1 over square root of LC. And we define this as omega naught, so it becomes R times C times omega naught. That is also the value of Q. And these two are equivalent. Another way to do this is, let's see if I can figure out another way. Another way is to have this write down as square root of R times square root of C square root of L. If I okay, how do I go over that? Okay. Okay. You know what? Another way to do this is write this down as C and C, and let's see right here. I have it in terms of having cancel out C. Oh yeah, I figured that instead of C, if I multiply this by square root of L times square root of L divided by L, what I'm going to have is one of these will cancel out. I'm going to have R times square root of L times C divided by L. What I do know is omega naught is 1 over square root of LC, so I can write this down as R divided by L, and since square root of LC is 1 over omega naught, putting these two, we're going to have an omega naught right here. That is another expression for this Q. Okay, so basically I've shown a few ways of finding the Q factor and one way of finding psi. Okay, moving on from that part, let's move on to part C. After we try to find the Q in different ways and different expressions for it. And for psi as well. What it's asking us to do right now is to use MATLAB or any tool that we want to do to have a value of inductor 265 millihenries and for capacitor a value of 26.5 microfarads. You have to plot a transfer function of this for three cases: r equal to 10, r equal to 100, and r equal to 1,000. Going back right here, I know this is going to be the expression for it. Let me box this one more time. And I'm going to use the same expression. So remember, this is going to be L over R and LC and 1. So if I do put this in terms of x squared and so on, assuming that the omega is our x, you're going to have a LC like x squared plus, sorry, you're going to have something like LC x squared plus L over R times x plus 1 over this. To simplify, I'm just going to write J omega as x. And I'm going to switch my windows to MATLAB and show you how to do this. All right. We are in MATLAB, and I've put in the values of L as 265 millihenries and C as 26.5 microfarads. The values for load are 10, 100, and 1,000. And I've calculated the transfer function for each one of these. Numerator, I have a 1. And then for j omega squared, I have L times C. And then for j omega, I just have L over RL, and I'm indexing to each one of these. And then for the last term, I just have a 1. So if you look at this, it's just an array having 3 terms of transfer functions. 1, I'm using RL1, which is 10, and this is using RL2, 100, and RL3, 1,000. Press right here, it's going to show up all the values for RL. And then I'm just going to say, plot this in a figure, and hold on to that figure until I plot 1, 2, 3 body plots, and then I'm going to hold off, and I'm going to show you that these are the values for each one of them, and we're going to compare them all. So say run section. Okay, that is run. Say run section. Apologize if this is not going well. Trying to plot these bodies. then now you can see all of that, and I'm just gonna run this section quickly as well to show the which one of these are which resistor values, because we have the LNC as constant, and the only thing that's changing is um, the value for uh, LNC. Okay, well, looks like I messed up a little bit. So I'm gonna do this. I'm just gonna say come back right here. I'm just gonna say run. So it runs all of them together. Yeah, run, and I'm gonna stop right here because I don't want it to go too far. All right, that is fine. I'm looking at my other screen, so I'm sorry I'm not switching the camera. So if you come right here, you do note that the value that we found for the Q was something like this. Um, we found the value for Q to be equal to R times square root of C over L, right? So what you could see is when you increase R, you see that the resonant frequency, which is right here, you see you have different peaks. As you increase R equal to 10, you can see it's pretty low right here. It's like around negative 20 dB, or 30, 25 dB. And when you have it at Q, you increase R to 100, so Q increases by a factor of 10. You're going to see from negative 20 dB it comes to 0 dB, which 0 dB is a value of 1. Negative 20 dB is a 0.1. When you put R as 1000, then you should see a factor of from 100 to 1000, a factor of 10, which is another 20 dB. So this should be the value for R equal to 1000, which is as shown right here, and that is going to be around positive 20 dB. This is the phase plot, and I don't think you should worry about it as much unless you're taking circuits classes that are going much further into these and signal processing talk about these. But right now we're just focusing on the magnetic plot, which is in dB, and showing that the R is directly proportional to the quality factor. And as you increase R, you see that the resonant frequency, the Q, is going higher and higher and higher.